Since the telescope was invented in 1610, the astronomer's lens has been partially obscured by the Earth's atmosphere. He has always carried his telescopes as high as he could.
The Earth seen whole is a compelling reminder of the need to safeguard our earthly resources.
To predict, and perhaps someday to control, changes in weather and climate is of the utmost importance to man everywhere. The ocean.
The air and atmosphere, fresh water, ice packs,
Crops, forests, mineral deposits.
pollution. Each has its own type of impact, but always they will be there.
The X-15 aircraft.
She's not the queen of the hangar anymore, although she's still hard at work.
Carrying a heavy payload of instruments. Undertaking studies of the near-space environment, possible before only with unmanned satellite and rocket-borne probes.
There's hardly any atmospheric pressure at all. So that's when some of those high-altitude experiments were performed. One of the airplanes had wingtip pods on with experiments out there, sometimes a camera, sometimes a sampling device for a high-altitude or micrometeorite.
Dryden's SR-71 was used as a science camera platform. An upward-looking ultraviolet video camera studied a variety of celestial objects in wavelengths which are blocked by the atmosphere to ground-based astronomers.
Every object on land or sea emits visible light, heat, and other radiation which can be measured.
High above the ground, we can more clearly see nature at work.
Advancing our understanding of the Earth as an integrated system.
Earth observations, stratospheric sampling, and testing of future shuttle or satellite instruments.
If it takes $1 billion to launch a satellite, you want to make very certain that your instrument works properly.
Plane and satellite complement each other.
Not only for validation, but also to acquire data that you simply can't get from satellites. Vertical profiles, high-resolution measurements.
In situ data.
Actually sample rather than to try to observe this from 100 kilometers away in space.
The sophisticated airborne research platform supports scientific investigators involved in a wide variety of disciplines.
Our first goal is to underfly the ER-2 up and down the Scandinavian coastline, look at CLO and the nitric acid
With a big aircraft that can carry many different instruments, we not only measure the ice surface elevation, but we have also ice-penetrating radar instruments that allow us to actually look through the ice, find out how thick the ice is.
In this case, we're measuring the rain and snow.
It's incredibly versatile and sturdy platform. It allows us to fly high or low, and it can carry a very nice complement of instruments. It will provide direct information about the nature of these fronts and atmospheric rivers. This information can be analyzed directly by the modelers to understand where can they improve their models.
Things that study nature, they don't ever do exactly what your plan was.
Measurements we make and impacts will help us improve forecasts. It'll also help us improve how we measure from space.
Winter storms, intense rain activity on the West Coast.
We're trying to get an understanding of the thermodynamic state of the atmosphere.
NASA deployed its piloted DC-8 and unmanned Global Hawk aircraft in a massive effort to collect as much data as possible.
It costs about $1 million per linear mile of coastline. We mispredict the landfall of a major hurricane.
We expect that these measurements will enable hurricane modelers to improve their track. The involvement of the Global Hawk is a game changer.
You can use this plane to do reconnaissance. Science is just a different kind of reconnaissance.
A combination of endurance, range, and altitude.
We're above the weather. We can study it with all our sensors from on top.
Satellites in low Earth orbit only provide a very brief glimpse.
With the Global Hawk, the expectation is that because of its 30-hour flight duration, we're going to be able to be out over storms for up to 20 hours or so.
Similar remote sensors that you might fly on a satellite, and then you're bringing it down to a 60,000-foot level. That's like putting the whole storm up into higher resolution.
We will start setting out specific flights to address things like air quality, aerosol over polluted areas.
Measuring the atmosphere from pole to pole, doing vertical profiles from approximately 42,000 feet down to 500.
What does the atmosphere look like? We'll quantify 100 gases.
250 different chemicals and ultrafine aerosol. Most can't be measured by satellites at all.
Where does ozone go to be removed from the atmosphere?
We can do things for climate and air quality if we decide we want to do something about that.
Science has a mission to measure atmospheric carbon dioxide during all times of the day and night.
You don't realize how fun it is to be flying 500 feet off the ground. This big DC-8 that kind of scares everybody in the neighborhood.
The DC-8 has some of the best measurements of CO2, methane, and other greenhouse gases.
We get to see where the different layers are as we change altitudes during the campaign.
What happens when this air mass gets up into the stratosphere?
From the overshooting cloud tops of thunderstorms, see how far different chemicals have penetrated into the stratosphere. When things get that high of altitude, it gets into more of the global airstream, and things can go downstream very quickly and start circulating around the globe.
I can't think of another airplane that could carry this many sensors and fly at those altitudes and do that kind of a mission.
ER2 acts like a steerable satellite for us. By studying the interactions between clouds and aerosols, we can better forecast models of climate.
These atmospheric trace gases are important because they affect the formation and destruction of ozone in our atmosphere.
How winds couple with convective systems to really either inhibit or accelerate their growth.
Never before have we been able to fly a system that can measure water vapor, winds, and aerosols all simultaneously.
We're trying to measure every 300 feet as we go up in the atmosphere, and about every couple miles as the plane is moving along. So this is really detailed measurements that you would really only be able to get aboard an aircraft like this.
The DC-8, it's really an airborne laboratory. You're chasing things like winds, they're fairly dynamic phenomena. There's a lot of times when the objectives will change or the area that they're wanting to look at is moved based off of what they're seeing, and we have to try and make that happen in real time.
The aircraft will take off from the Dryden Flight Research Center and then fly over the western United States using its infrared camera to find and actually map out fires.
We will get
real-time information from that scanner that's related to the thermal emission coming from individual fires.
The U.S. Forest Service can use that data to help plan out their resources.
The nice thing about the radar is it can see through smoke, it can see through clouds. So it's an all-day, all-night imaging technology.
The FireX AQ team will deploy throughout the U.S., taking measurements of smoke from wildfires.
The purpose of this overflight was to collect thermal and visual imagery of some study caves that we have located in the Mojave Desert. By being at 3,000 feet, we were able to have good coverage as far as the landscape is concerned. Through developing techniques for detecting caves on Earth, we can then take those techniques and use them to look for caves on Mars.
There was an earthquake about a week ago. We're surveying that area to see what ground movement has happened since the earthquake.
The objective is to prove the technique of simultaneous measurements of ocean currents and winds from the same instrument. Both ocean currents and winds actually influence Earth's climate, and they influence each other. This should be a path forward for the next generation space mission.
The main goal of the mission is to measure as precisely as we can the vertical exchange that the structure produces between the surface and the depths of the ocean. The structure we're trying to see are small, and satellites today are not capable of having this level of resolution. That's the beauty of planes. It allows us to have way higher resolution.
Pretty neat mission. We've been flying around at 28,000 feet. The biggest challenge we have flying these type of missions out here are staying on these exact lines as we fly over the wetlands.
The G3 is an excellent platform for this work. Its speed, its range, it's an easy work environment as you can see in here.
You can go wherever you want, whenever you want.
And also we can have a different look angle compared with satellites.
Dryden engineers developed this repeat pass capability, which is our platform precision autopilot, which enables us to fly a line in the sky today, and then tomorrow, a week from now, a month from now, a year from now, we can repeat that line every time to within plus or minus 5 meters.
Couples the radar to the flight track of the aircraft.
Right now, the pilots aren't even flying the airplane. It's completely hands-off. This right here is actually flying the airplane.
Flying these lines over and over will allow us to study the wetland change over time.
We can look at how natural deltas form so that we can understand more about sediment deposition and maybe try to reverse these loss of sediments in many of the other deltas around the world.
What we're really out here doing is we're trying to understand how much water, how much sediment, and how much carbon is moving from North America out into the coastal ocean.
This time around, we're focused on forested biomes. The main question we're trying to answer here is how much carbon is stored in a forest ecosystem.
These trees are amazing because they really are the connection between the land and the sea.
Today we are over the Arizona area to look at the next slide.
Measuring the heights of the levees against high tide and low tide.
You get information about where the levees are weak. It's very economical to use science to determine where to best use your resources. We could tell when a sinkhole is forming before that catastrophic failure happens. We can try to image the oil spill and the effects on the coastline.
Looking at glaciers as well as volcanoes, which will then go on and help us do some predictive analysis in the future. A lot of it is supporting private organizations, universities, other NASA centers, but we actually have the teams and the tools to be able to take a science instrument like this UAV SAR pod and put it up into the environment where they need it.
The ER2 is a very unique aircraft. We can get a very wide swath with these super high-tech instruments. We're kind of the last step in development on some of our Earth science satellites. We actually take it up to extreme altitudes and cold soak it and put it in an extreme environment.
We're here to study the volcanic plumes from Kilauea volcano. And we can have a real impact on helping people to manage this risk if we can make the measurements and give them the information they need.
Knowing the spectral signature of what you're looking for can help you ascertain the health of a system.
Different types of coral have different spectral signatures.
We believe we'll be able to say something about where the coral resides and how healthy it is.
We want to make sure that we're using our technologies to also help the planet and understand processes on the planet.
This basically gives us almost the same view of the moon as Earth-orbiting satellites would have. We want to know this to a high level of accuracy because we essentially are using the moon as a benchmark so that Earth-observing satellites can turn and look at the moon and set the scale on the amount of light they're measuring from the Earth.
We were beautifully set up to see this. We were just well positioned. Aircraft performed perfectly.
What Armstrong is doing to go out there and facilitate science missions such as this Eclipse mission, these involve detailed logistics, flight planning, modification of aircraft.
We're able to see the eclipse for a little bit longer than others might. We control our timing exactly so that we enter that region of totality right when it starts, fly as slow as we can through it, and get the maximum amount of time on that target.
You don't have to be a scientist to really be transformed by the beauty of a total solar eclipse.
Moving beneath the telescope.
It's an amazing engineering feat, I think, that door back there is big of the hole that it makes. When it opens, you don't even notice it whatsoever.